Roger is going to be speaking about higher dimensional contact submanifolds. And well, you can use extra 5 minutes that we took from you. So welcome for coming.
Okay, hi everybody. Does everybody hear me properly? Okay, if the volume of my voice, the font, or my words are inadequate, just let me know, okay? So, as Renato is saying, I'm going to be talking about contact submanifolds, and the idea is we understand very well three-dimensional contact topology, and in particular the study of submanifolds there, which means the study of knots. So that's three-dimensional knot theory, which can be Legendrian or can be transverse. Now, the higher dimensional world, it's been quite unexplored in the context of contact submanifold, but the last 2 years have seen some developments, and in particular I was interested in two problems, that's not rare, existence and uniqueness. So in this talk I want to present the developments of this last year in which the solutions have been achieved, and the goal is to explain what is the existence problem, what is the uniqueness or non-uniqueness problem, state the theorems that solve that, and explain the proof of them to the extent that time allows that. Okay? Again, if there are any questions regarding the context, just let me know. By the way, for experts, smooth will always mean almost contact and smooth. So every time that I say a smooth isotopy, it means an almost contact and smooth isotopy. So everything related to formal geometry, algebraic topology, I'm just saying that that's smooth theory. Okay? So let's start with the existence problem, at least what is the statement. The existence question is about whether a given submanifold can be moved, can be isotoped to be a contact submanifold. So the existence question asks, suppose that you have a contact submanifold, sorry, a contact manifold, so that's Y. So this Y is always going to be of dimension 2n plus 1. So this is contact. Then you can ask the following. Suppose that you have an embedded submanifold. So suppose that you have a smooth manifold M. Typically, it's going to be of dimension 2 less than that one. The higher codimension is perfectly allowed. It's just not as interesting. So suppose that you have a divisor of this kind, and so that means that this is a smooth embedding. Suppose that this is a smooth embedding. Is it possible to find a smooth isotopy of this embedding? That is to say, is it possible to deform the submanifold M such that at the end the submanifold M is contact itself? Okay? So is it possible to find an embedding I prime which is now isotopic to I, but this embedding is now contact? So to find this contact with I prime isotopic to I. So with I prime isotopic to I, and again, I won't remind you of that again, but isotopic means almost contact isotopic to I. Okay? So that's the question. Is the question clear? I give you your favorite submanifold. Take an S5 and take your favorite knotted S3. Is it possible to deform that S3 such that it becomes contact? Now, yes? Yes, yes. Every time that I say smooth submanifold, it means an almost contact submanifold.
What is an almost contact embedding?
An almost contact embedding is an embedding such that when you push forward the structure in here, it is an almost contact, the structure group lies within the structure group. So the UN times 1 reduction reduces to the UN minus 1 times 1 reduction. Does that make sense? So the almost complex structure is compatible. Okay. So one setup in which this question is rather understandable is in 3 dimensions. In there, you're just asking, if I give you a knot, say in S3, is it possible to make it contact? In 3 dimensions, contact just means being transverse to the distribution. So that's oftentimes called transverse knot. And it's a nice exercise in Geiger's book, section 3.3, that it shows that every smooth knot can be made transverse. Okay? So you can do that in 3D in a rather easy manner. In higher dimensions, it had remained open till now. And in higher dimensions, I should add, there's a slightly stronger question that you can ask, which is, suppose that I give you not just a smooth manifold M, but I give you a contact manifold M. Is it possible to find, given any smooth submanifold, an isotopy which makes the embedded submanifold now contact n with that prescribed contact structure. Does that make sense? I'm saying two things now. Not only the embedding is going to make it contact, it's going to make it contact with the structure that I want. Okay? So added to that, is it possible, so that's like, this would be called the isocontact H principle. This would be just called the contact H principle. So is it possible to prescribe the induced structure? Is it possible to prescribe M? So let's maybe call this M xi sub M. For knots, this is easy because there's a unique structure in the circle. So when the circle is transverse, it induces the unique structure in the circle, and you're done. Any questions regarding the existence question? I'm going to now make some remarks when it's easy, when it's known, and what is left to do. OK, so now what do we know about this theorem? So thanks to the work of Gromov, his thesis actually, we know that the existence question can be solved as long as the codimension of M inside of Y is large enough, meaning 4 or more. So remarks, the first remark of all is to say Gromov's H principle says that it's possible if the codimension of M is at least 4, so that's the codimension of M inside of Y, then yes. And it should not be surprising that the codimension 2 phenomena are the hard ones. Okay? So if the manifold M is open, or in particular if M is codimension 4 or more inside of Y, you know how to do that. Okay? Now, as I said, the three-dimensional case, so the 3D case is also achievable by hand. And again, notice that both questions are the same in the three-dimensional case. They're definitely not the same in higher dimensions. OK, so I'm not going to write that in the board because I need the space. But I want to mention that there's been some work in dimensions 3 and 5 by Yankee, Lekili, and John and Nair. And Nair and Furukawa have said something interesting about braided embeddings. Pancholi, Pandit, and independently Lazarev have also done some work regarding the prescription. But yeah, all these are very interesting works, but my goal is just to state the question and solve it, and to state the next question and solve it. Okay? You can ask me about those works. I should also mention Onda and Wang, whose convex surface theory in higher dimensions also helps addressing these problems. Okay, uniqueness question. Well, if that was pi0 surjectivity, this is pi0 injectivity. Uniqueness question is I give you two manifolds, which I know they're contact. And then I ask you, if I know that these two manifolds are smoothly isotopic, each of them is contact. If they're smoothly isotopic, is it possible that they are contact isotopic? Does the question make sense? So is smooth topology very different from contact topology when you look at nodes or contact submanifolds in the higher dimension? Okay, so let y0 and y1 be two embeddings of the same contact manifold. Again, Cm inside of this. And these are contact embeddings, so be contact embeddings. And assume they're smoothly isotopic. That means that in the diff category, I0 is the same thing as I1. Question, is it true that this thing holds in the contact category? So is it true that it must be that I0 is the same in the contact category as the contact isotopy to I1? Okay? So in the classical theory of 3D case, we know what that is. That's the statement of simplicity of transverse knots. If I give you, say, two figure-8 knots, okay? I have a figure-8 here, a figure-8 there, and I know that each of them is transverse. Smoothly, they're isotopic because they're figure-8s. Are they transverse isotopic? So in the case of figure-8, we know the answer is yes. But the point of rigidity of contact topology, and that was the theorem that started contact topology with Daniel Benekan, is some nodes are different from others, even if smoothly they are the same. So there are classes, smooth isotopy classes of nodes, which have different transverse representative, which means the same smooth node might have different transverse representative, which are not transverse isotopic to each other. Okay, the question is, does this rigidity still hold in higher dimensions? And this is what we're saying. So in here, this was an exercise in Geiges. This question in 3D was solved by Berman and Menasco, and that's a pretty decent paper. So in the 3D case, this is achieved by hand, and this is a theorem of Berman and Menasco. So the non-simplicity, which means the non-uniqueness, clearly, you're interested in non-uniqueness. It's much more interesting because it tells you contact topology is different from smooth topology. The non-uniqueness in 3D is due to Bill Menasco and John Berman. So that's Berman and Menasco. And I'm very happy to lecture about this theorem because I really like it. It's a very simple operation called a negative flipe. It's just a 3 braid, and it does some change whether the twist goes here and there. They just switch it. Same smooth type, very clear, but there's some magic that tells you that the transverse type, and that's very specific of 3 braids, it's not the same. Anyway, this is a really nice paper to look at. OK, so I think I'm done with the remarks. So this applies to this. And finally, again, Gromov principle is an H principle, so it applies for this in codimension 4, and it also applies for this in codimension 4. So if you were to have two S3s inside of S7 and ask, oh, look, this S3 is contact, these other S3 is contact, are they the same? Answer, yes. Okay? The only interesting case are the codimension 2 cases. Okay? Does that make sense for everybody? Okay, great. So let's now address the solutions to these problems. I'm going to start stating the solution to the existence problem, which is good news. Well, I don't know. I think it's good news. So out of the 2 papers, this is the existence is addressed in the Pancioli presses, in the work with Pancioli presses, and the uniqueness I did with John and Nair. OK, so theorem, and that's existence theorem. And I want to emphasize the word isocontact, because isocontact means that actually it also answers this question. So isocontact existence. Well, the short statement is the answer to this question is yes, and the answer to this question is yes. I'm still going to state it properly, but that's the punchline. Okay? So let M and psi M. This is going to be codimension 2, again, because in higher codimension, I would just have used Gromov. So you take these 2 contact manifolds, B contact, and then you pick smooth embedding. Again, smooth means almost contact, and this is smooth embedding. Then there exists a contact embedding. There exists Y prime in the same contact class with the prescribed contact structure, which solves the problem. Then there exists this guy, which is contact and I prime is diff to I prime. Statement clear for everybody? Just to give you a rough idea, one could really think just as the space of embeddings of M inside of Y. So you could say, well, let me take all the smooth embeddings of M inside of Y and then ask which of them are contact. And you're going to have potentially some classes. So that would be the equivalent of the mapping class group, the pi0 equivalent in the case of embeddings. And then the question that you're asking is it possible to get into some of these classes? Like if I give you an embedding here, is it possible to move it down here? And obviously this question is, if I give you this guy in here and this guy in here, are they connected or not? So that would be pi0 injectivity. OK? OK, I'm assuming everybody's happy with this theorem. Yankee? Yes?
Suppose y is S5.
Yes?
And checking that whether there is a smooth embedding is equal to C1 0?
Yeah, the first term class is 0. The first term class of M. Yes. Yes. Yeah. Yeah, so yeah, in the case of S5, thanks Yankee, smooth, where by smooth I mean smooth and almost contact. Smooth doesn't mean anything, it just means there exists a smooth embedding. And almost contact is just detected by the Chern class. In general, it's going to be some vanishing of some classes giving you obstructions. But it is algebraic topology. OK? Good. So this addresses this. And now let's explain the solution to this problem. So historically, this was done first, and then I did this. The reason I did this first is because imagine, I don't know, like to me this tells you contact topology in higher dimensions is also interesting. Like contact knot theory in higher dimensions is interesting. And then you maybe want to ask, well, does it exist? Okay, but I mean, we already have some examples. Okay, so the theorem, that's uniqueness. Well, I should call it rigidity or non-uniqueness. Is that in any dimension you can find many examples, in fact, infinitely many examples where this breaks down. Okay? So in any dimension, you can consider even the simplest ambient submanifold. So this is a standard sphere, which hopefully you've studied in the summer school, the standard sphere. B, the standard sphere. Then there exists a manifold, so there exists M and psi M in codimension 2, that's 2n minus 1, and 2 embeddings, so that's y0 and y1, which embed M in whatever smoothly interesting way inside my sphere, in a way that these two guys are smoothly isotopic but not contact isotopic. And 2 embeddings, so this is 2 embeddings, 2 isocontact embeddings. Such that y0 is diff I1, but, and that's the rigidity statement, as contact embeddings, they're not the same. Okay? And this question is addressed by this theorem. Okay? Are the blackboards clear? I've now presented the two questions and stated the theorems that solve those questions. The goal of the rest of the talk will be to present the proof of this theorem first, and then, as much as I can do, present the proof of this theorem as well, Elsa. Isocontact, I just mean that this is actually prescribed. In this precise statement, it really doesn't matter. I'm just saying I don't know. There was a whole discussion between Gromov and Asperger, things we call symplectic embeddings, isosymplectic embeddings. When things are prescribed, you call it isosymplectic or isocontact. Okay? So we're now going to veer towards the proof of this theorem and then the proof of that theorem.
Can this be done with M being a sphere also?
Yeah, this is a fantastic question. The answer is I currently don't know, but I strongly believe the answer is yes, which would prove a really good counterexample to the non-simplicity of the standard and not in. I claim it's not known, but my conjecture is that not only it can be done with M being the sphere, I think it can be done with M being the standard and not. It's just the equator of an equator. Okay? Does that make sense? You take this as sphere, S5, and now you take the equator of the equator, which is an S3. That's a very specific smooth isotopy class. I claim that it's possible, very likely, to find two contact standard S3s inside of S5s, which are not contact isotopic. So this is known to be false in dimension 3. In dimension 3, a Legendrian or a transverse knot is always the same. Okay? But I think in higher dimensions it breaks down. I don't know. We can discuss that. It can be, I can get an RP3. And then you kind of want a double cover. But I'll give the arguments for that another day, maybe. OK, so let's gear to the proofs. And you might want to keep an eye on the proofs that it really does not work in the symplectic setting. So these two problems are also outstanding problems in the symplectic setting. This is known already in CP2 as the symplectic isotopy problem. And this, I don't know how it's called, but it's a hard problem. Okay? So if you were able to solve this in the symplectic setting, we would really understand both contact and symplectic. But the proofs that I'm going to give are really, really contact proofs. And I have no idea how to make them symplectic. But it'd be real interesting to me. OK. So proof of the non-uniqueness, which means let's build a counterexample to the fact that there would be a unique isotopy class, contact isotopy class inside every smooth isotopy class. And instead of proving that completely general theorem, well, rather general theorem, where I even said there exist infinitely many, so this is infinitely many, I'm going to prove a slightly simpler theorem, but it also answers the question. So toned-down version of that theorem. So counterexamples for uniqueness. This is the simplest counterexamples I know. And it states the following. It says in the standard sphere, there exists two embeddings of M being very particular. So this is still standard. So this is standard, 2m plus 1, size standard, B standard. And let's now take M to be the unit cotangent bundle of Sn in this dimension. So this is going to be now the unit cotangent bundle of Sn with its standard contact structure. So this is unit cotangent bundle. You can put a metric. You can think about an ideal boundary, whatever works for you. And then the statement is you can build those embeddings with this kind of manifolds. Then there exists I0 and I1, which go from this unit cotangent bundle with its standard contact structure, which are not simple, meaning they're smoothly isotopic, not contact isotopic. This simplicity is this thing. So this sentence usually in contact topology, it's called simplicity or non-simplicity. That's not simple. Simple means the smooth type determines the contact type. So this means they're different. Okay? Okay, so I'm going to build those. Something rather interesting about these two theorems, and this literally is my lack of imagination, is that they're both proven using Legendrians. And this is a topic that has been in my life for a long time. And every time that I start with a problem and I don't know what to do, I kind of look for a Legendrian. Now, it might be that you don't see a Legendrian here and that you don't see a Legendrian in the existence problem. My solutions are going to offer a way to do it which really depends on using Legendrians. So okay, here's the idea for this very simple class of counterexamples. Well, I'm going to start with Sn inside of this standard S2n plus 1, and I'm going to ask that Sn is actually Legendrian. So let's go for the proof of that in the first ingredient. So the first ingredient is how do you construct this thing? So ingredient number 1, the candidates. And the idea is, well, let's pick a Legendrian sphere inside S2n plus 1. And what do I know about Legendrian spheres? I know they're rich. I know they're interesting. I know that 20 years of floor theory tell me that there are Legendrians which are smoothly isotopic but not Legendrian isotopic. Maybe I can use that thing that they're different Legendrians to cook up something which is a contact manifold and they're different as contact manifolds. Okay? And that's how it's going to go. So the candidates is choose inside of the standard sphere lambda to be the standard Legendrian or not. So that's just the boundary of a Cn inside of the, sorry, Cn plus 1 inside of the Cn. Okay, so this can be imagined like the boundary of a complex space Cn plus 1, pick inside of it a real Rn plus 1, and now look at the intersection with the sphere. That's going to give you a sphere. That's this Legendrian sphere. So choose this to be the standard Legendrian or not, boundary of a standard Lagrangian flat disk. As the standard knot, as the standard Legendrian knot. And now I'm going to show you how to construct a contact manifold out of a Legendrian. And that's a really simple operation. What do I know about Legendrians? Well, we know that a neighborhood of a Legendrian inside a contact manifold looks like what? Looks like the jet space. So it looks like J1 of lambda, and by that it's meant to be, and these are all contact homomorphisms, the cotangent bundle of lambda times R. This is the red direction in the standard contact form. So then, inside of here, what I see is that I can choose a special contact manifold, namely the unit cotangent bundle here times any level set that I want. So then I can check that the sphere bundle given by T star lambda sphere and 0 level set is a contact submanifold. Now, nothing that I've said really uses that this is the Legendrian and not. Okay? This is always true for any Legendrian. And now you can warm up your topology, whatever, your topology muscles, and ask what would that be for like S2. So if I have an S2 inside an S5, then I'm going to get an RP3. So here's a way to cook a lot of contact RP3s. Choose your favorite Legendrian 2-sphere in S5. Look at the unit cotangent bundle. There's the contact RP5. What about S4 or S5 or S7? Things get sometimes interesting. In the case of S3 inside of S9, S3 has a trivial tangent bundle, which means that the contact submanifold that you obtain is of the form S3 times S2. Okay, so a lot of S3 times S2s inside of S9. Okay, and then it doesn't have to be a Legendrian sphere. When I give this talk, for a whole hour, just this proof, you can also do it with tori. So a very interesting thing that I like to do is take two Legendrian tori, T2 and T2 inside of S5, and now do this construction. You get two interesting contact T3s inside of S5. And then if the Legendrian tori were not Legendrian isotopic, and there's lots of ways to construct it. Georgios, I don't know where you are, but he has like several papers on that. Yeah, there. If you take any of these interesting Legendrian tori, then you will get interesting T3s contact embedded in S5. Okay? So more or less, the sketch that I usually do is that I think of my Legendrian as being somewhat in here. Like my Legendrian is flying in here, and around it, and it's very hard to draw in the front, obviously, but around it, there's this unit cotangent bundle. And that thing is contact, so that's contact. Okay? So how do you pick two interesting Legendrians? Well, the Legendrian and not is one Legendrian. How do you pick another one? You really have an infinite amount of choices. For this talk, let's just pick a stabilized Legendrian and not. So you take the and not, and you just add a slightly small modification here, like a zigzag. Okay? For the experts, what you would really do is you would take an annulus and then push it up, so that preserves the formal Legendrian class. But the idea is that there is a very easy way to modify this Legendrian to make it Legendrian different, though it's smoothly the same. Okay? So the candidates are going to be the standard Legendrian and not, and then its contact friend, call it whatever, and the stabilized Legendrian and not, and then its contact friend. Does that make sense for everybody? Okay. 5 dimensions is a good dimension to be thinking on. Okay? So now let's proceed with ingredient number 2, which tells you, fine, I've now told you how to construct a lot of interesting contact submanifolds. How do you really know they're interesting? Why are they different? Why aren't they like all the same at the end of the day? And this is where ingredient number 2 comes in. So ingredient number 2 is a technique based mostly on contact surgery diagrams, which tells you a way to distinguish these contact manifolds. So ingredient number 2. The contact branch cover. So that's surgery. That means contact surgery diagram. So surgery diagrams for branch covers. So what's the idea here? The idea is, imagine you pick two Legendrians, you look at the contact friends, and now you say, how do I distinguish them? How do I know that these guys are not contact isotopic? Well, here's an easy fact. If they were contact isotopic, then the contact branch cover of one and the contact branch cover along the other would be contactomorphic. So if I show that by branch covering along one, I get a contact manifold, which is not contactomorphic to the one that I obtain by branch covering along the second one, then they could not be contact isotopic. Does that make sense for everybody? And smooth topology is absolutely standard. Like you take two knots, you branch cover along one, along the other, oh, they're not the same smooth threefold, then they're not the same knot. That's a pretty easy way to do things. But now it's the same smooth setting, but different contact setting. So how do you decide whether the branch covers are themselves not contactomorphic? Because you just like kick the problem down the road. Well, one way to do it is to actually pin down those contact manifolds. And to me, one of the most useful ways to pin down contact manifolds in higher dimensions is through contact surgery diagrams. So here the statement is even better. Not only do the branch covers have nice surgery diagrams, but the contact branch cover, say the twofold branch cover, is Stein fillable. So these contact manifolds are both Stein fillable. So let me state that. The twofold branch covers of any tau sub lambda, and I'm going to define this guy to be this tau of lambda. I usually like to call that the contact push-off, which is not to be confused with the transverse push-off, because they're not the same thing. Okay? Transverse push-off is only a piece of this contact push-off. Okay? In 3 dimensions, this is a 2-component link. The transverse push-off would be a 1-component link. But this thing, it's what I like to call the contact push-off. And what you can ask is, imagine I have a submanifold which is a contact push-off. How do I branch cover along it? The answer is here. The twofold branch cover of any tau of lambda is Stein fillable. And it has a really nice handle body decomposition. So this is a proposition, if you wish. So this is the main proposition. Prop. That's this sentence in here. And a Legendrian handle body diagram for it is given as follows. Well, you start with your lambda. That lambda can have whatever front it wants to have. Here's the front for lambda. And now usually you understand this lambda. You know how to compute LCH, you know how to do generating families, something. So how do you obtain this Stein manifold which is bounding this contact branch cover? The claim is that you just take this front, you do this, and that is, by the way, topologically a connected sum, and you just add the very same front on the other end. Is the statement of this proposition clear? I'm going to give an intuition of why it's true, but is the statement clear? Yes, Elsa. Yes, in higher dimensions, yes. Yeah. So, yes, Luis. Sorry?
What's the contact branch cover?
As an operation, or so it is a smooth branch cover, but a smooth branch cover can be upgraded to have a contact structure on the upstairs manifold if the locus along which you branch is contact itself. And the way you do it is away from the locus, it's just a finite cover, so you just pull back the contact form. And then around the local model, you can just write down the contact form directly. And Geiges, Gonzalo, and company did that back in the 90s.
Is it always branched? For example, in the RP suite case, say here, wouldn't that just be a suite and it's not branched?
No. OK, wait. OK.
Yeah, we don't know what's the tuples. I don't know.
OK. So lambda lives in the standard sphere, right? Lambda lives here. Lambda lives in a sphere. Now, where does tau lambda live? This guy also lives inside of this sphere, right? Because it's a neighborhood. Because this piece lives in the sphere, this also lives in the sphere. Right? So you have your ambient sphere, S5, and you never touch that. Now, inside of it, you find a Legendrian. Now you find the blurb friend, which is contact around it, which in the case of a Legendrian S2, that's an RP3, which is contact. So right now you have obtained a contact RP3 inside of S5. Now, smoothly, you can take the S5 and branch cover it along RP3. Okay? And that produces a 5 manifold. Okay? That 5 manifold, well, you'll see that it's actually the unique cotangent bundle of S5, whatever. It's a smooth manifold. Okay? What I'm saying is, not only am I going to give you a Kirby diagram for that manifold, I'm going to give you a Stein filling of that manifold. So I'm going to give you a Legendrian handle body for the Stein manifold that bounds that contact structure. So there's something subtle if you've thought about it in the 3D case, which is usually when you take a transverse knot and a stabilized transverse knot, and you branch cover along the stabilized one, the threefold becomes over-twisted. note that this is not the case here. Even if I take a stabilized Legendrian, tau of lambda is not going to have an overtwisted branch cover. In fact, it has a Stein-fillable branch cover. Okay? So that's the key difference between taking the positive transverse push-off or the union of the positive and the negative transverse push-off. Does that make sense? So in the 5-dimensional case, we take S5, an RP3 inside of it, and branch cover along this RP3. See what we get. Now, the point is that RP3 is not any RP3. It's an RP3 that comes from this construction. It's tau of lambda. So for a branch cover whose branch locus is a contact push-off, I can tell you what the contact manifold is. It's the boundary of this Stein manifold, if it's a two-fold branch cover. Okay? The paper in general has n-fold branch cover, more general. But this is the simplest possible case. Chris?
Can you just explain quickly what the diagram actually represents?
Yes. So lambda, so this is a front picture, front diagram in R to m plus 1. So the idea is the following. Your Legendrian lambda lives inside standard sphere, 2m plus 1. Pick a Darboux chart that contains it. It misses a point. It has a front diagram. Okay? So that front diagram is the one that you insert exactly here. And then you do a zero surgery, a one-handle Legendrian thing. So that in the front, that would be something like that. It would be something like that. Does that make sense? It's like an unknot times an interval. It's a connected sum in the front. And so you take this diagram, you take this diagram, pick whatever cusp you want here, the cusp edge, and then do this connected sum in here.
So
This
this produces another Legendrian.
produces another Legendrian.
Describing is a Stein manifold obtained by attaching a handle to that Legendrian.
Correct. Yes. Correct. And in the case that I'm doing today, where lambda is a sphere, that's still a sphere, and nobody will complain. When I give this talk where lambda is a torus, you have to explain what a Morse-Bot handle attachment is. But in this case, it is a sphere, so it makes sense to attach along it. That makes sense? OK. In the case of n-fold branch covers, by the way, you need 1 handles or n-1 handles. So this is a 2-fold branch cover of tau lambda as a 2n-1 dimensional submanifold inside of 2n plus 1 with the standard structure in here. Are we all set? OK. Good. So now, how do you finish that theorem? How do you conclude using this construction and this proposition on contact surgery diagrams that indeed, if I took, say, the standard Legendrian knot, and can I erase this? Or yes. And say a stabilized version of it, then you're going to get 2 different contact manifolds. Well, here you face a problem, which is we really don't know any invariants of higher dimensional contact manifolds. Some people are really good at obstructing fillings. Some people are good at doing contact homology maybe in 3 manifolds. But in general, contact homology, well, it's something you want to tread careful with. And symplectic homology a priori depends on the filling. However, sometimes symplectic homology, or its plus par, SH+, can be an invariant of the contact boundary, in the case of first chunk class being 0 and simply connectedness. So that's actually what's happening in these examples. So let me conclude the proof of the theorem. So proof of theorem. OK. So our 2 candidates are going to be the standard knot and its stabilized version. So consider the first lambda, so that's lambda 0, to be the standard knot. So that's going to be in any dimension given by this flying saucer, where the equator is of dimension n-1. So consider this the standard knot. And lambda 1, so that's the other candidate, and lambda 1 is going to be given by the following front. You just take inside of it an annulus, and it's hard to draw something in all dimensions at once, but mostly what this manifold is in here, it's a copy of S1 times the n-1. Okay? This is a sphere, Sn, and this is a copy of a manifold inside of it, which has Euler characteristic 0. So it's stabilized, so it's formally isotopic, but stabilized version. Okay. Classical way to prove these are not the same. This has the generating function. This does not have a generating function. This has the GA0, non-zero. This has the GA0. They're definitely not the same Legendrian. So now you hope that this construction, that tau lambda 0 and tau lambda 1 are going to be different. So why are these different? So why are tau lambda 0 and tau lambda 1 different as contact manifolds? Well, answer branch cover along them and see which contact manifolds do you get. So the twofold branch covers of the sphere along them yield the following contact manifolds, and that's where you use ingredient number 2, are the following, are the boundaries, the contact boundaries of the following 2 diagrams. So the first diagram is going to be what? Which is going to be this guy, 2 copies of it. So that's not very surprising. You just take this guy, that's a sphere, and you connect some with itself. Well, anybody who's had fun with Legendrian knots knows that this is just another knot, okay? So this tells you, for instance, that if you took this RP3 inside of S5, what you would get would be something which is the boundary of T star S3 as the new thing. So that's an S3 times S2. Are we all following? It's the first talk, so if you're not following, you should complain. You have the energy to complain. By the end of the day, you won't have the energy to complain. Okay. So this is figure for tau lambda 0 understood as the boundary of this Stein manifold, okay? Which, again, is just really as a Stein manifold. This is just T star as m plus 1. Okay? So what happens to the other one? The other one has this funky thing in here. So in here, you're going to get this funky thing. And now, well, sorry, I'm going to try it properly. And now, regardless of whether there's a connect sum or not, the point is this has clearly a flexible Weinstein manifold as its underlying Weinstein structure due to the existence of these charts in here, these zigzag loose charts. So this tells you that this still stabilized. So now you really have the hope that these 2 manifolds are going to be different. What is the argument? Now you can kind of choose the way you go. In this example, where the manifolds are actually Britzkorn spheres, you can just apply SH. So in this particular set of examples, the symplectic homology of this manifold, somebody tell me, what is the symplectic homology of this manifold? Is it 0 or not? Okay. Well, this is the cotangent bundle. So this is going to be the loop space, right? So it's definitely not 0. It is loop space homology. Because it's spin, loop space homology. Okay? And now the point, and now this is really the point, is that SH of this guy is non-zero. This guy is 0, but this does not tell you that the contact manifolds are different a priori. But because these are Furniture-class vanishing simply connected fillings, then you do know that SH plus is going to be an invariant. And in fact, there is a paper of Shao, which builds on the thesis of Lazarev, which itself builds on all the theory of simple, topologically simple Liouville fillings, that tells you that if this guy had any other filling, it would also be SH0. Okay? Did you guys teach SH last week? Okay, well, mostly the idea is SH contains information about the boundary and the interior. The interior is mostly the homology of the filling. The boundary is the so-called SH plus. Now, if any other filling has whatever SH it has, and you've proven that the SH plus are the same in the boundary, it mostly tells you that the SH of the interior must be the homology. There's no extra contributions in the boundary. And then you do the Smith connected sum argument to show that it must be 0. Okay? It's a rather simple homological algebra argument, and it tells you that any other filling would have SH0, so these 2 manifolds cannot possibly be the same. They're not the same as Stein manifolds, but the boundaries are also not the same. Okay, that was the easy part of the talk. Okay, so now you have a bunch of examples, okay? And you can build other examples by choosing other Legendrians, other manifolds. Instead of the sphere, pick another manifold, and things will go through. Elsa? Yes? Let's read this. So the twofold branch cover of this manifold along this is Stein fillable, and a Legendrian handle body diagram for this Stein manifold, for this Stein filling, is given by this. Does that make sense? Yes. If you're going to branch cover along something which is a contact push-off, there's a very natural Stein filling that you might want to consider, which is this one. I mean, yeah. In general, it might not be a contact push-off. Okay? Good. This endows you with at least one counterexample to the uniqueness thing, okay? And mostly a technique to build other ones. Yes? The only reason, okay, so this is the only reason for this. So if you want to obtain a Legendrian which is smoothly the same and formally the same, you can do this push move along a manifold. Now, the formal class will vary by the Euler characteristic of this manifold, which is, by the way, another thing that happens drastically different in dimension 3, because there's no zero Euler characteristic, zero-dimensional manifolds. Very deep fact. Okay, so now in here, in high dimensions, you can choose something that has Euler characteristic 0, and so this follows. They're formally isotopic. Does that make sense? If I just pushed along a disk, then these two Legendrians wouldn't even be formally isotopic. So, like, what's the point? Well, except that they're Legendrians. So almost Legendrian. I don't know, yeah. We never say almost Legendrian. We say formally Legendrian. No, so this is because it's loose Legendrian. So flexible Stein always has a set 0. Yeah, that's why I didn't want to call it zigzags. Because it has this thing, then it's flexible. I'm using a lot of machinery, but I don't know, just life. Okay. Any other questions?
The fact that you know this for target SN
yes.
Here, does it imply for other?
Yeah. So the answer is yes. I wouldn't say all manifolds. It certainly implies the same proof goes through for a subcritically fillable manifold. So S1 times another sphere, something like that. Any products of spheres, that's okay. If you have a filling, then you have to choose the Legendrian lambda such that you're able to say something about the symplectic homology of something which is now not just one handle attachment, but a more elaborate diagram. So you would have copies of the diagram itself of the filling, and then it would still be possible. So if you change that sphere by subcritically Stein fillable and even probably Stein fillable, same proof would go through. And in general, it's a good question to say you have these examples which are distinct in this sphere. Connect your favorite contact manifold with them. Are they still distinct? Well, somebody write a paper about that. Like, maybe there's some manifolds that when you connect them, they become the same. That would be interesting. Does that make sense? But yeah, good question. Okay, we have 13 minutes left. I don't know how we're doing on energy. Okay, good? Good, perfect. So now the goal is, now that we know that there is interesting contact knot theory in higher dimensions, let's declare an existence theorem. And the way I'm going to explain to you the existence theorem, given that I have 13 minutes left, is by trying to discuss the very main ingredient that is used, which again is a certain Legendrian that appears in the picture. So theorem about existence. Recall the following. It's that any smooth embedding be smooth, then there exists an embedding, so let's call this I. There exists I prime, even with a prescribed contact structure here, contact. And again, it's an isocontact case principle, so that's for any XM contact structure in M. Okay, so we're now relaxing, whatever, go to your good place, and we move towards existence. Okay, So as I said, no Legendre in here. But let me try to prove something which will imply this theorem. And it's, in my opinion, in itself interesting, which is a Whitney trick. So in smooth topology, there's like decades of interesting applications of Whitney tricks. And the claim is, I really believe such things should also be really useful in symplectic and contact topology. And there might be symplectic Whitney trick, contact Whitney trick, Legendre Whitney trick, Lagrangian Whitney trick. You pick your own. In my opinion, the useful one here was the Legendre Whitney trick, which is what I'm going to state right now. So the theorem that implies that theorem, and that's what I'm going to explain, how this implies that, is a version of the Whitney trick in higher dimensions where one manifold is Legendrian and the other is going to be contact. So let's state it very carefully. So let BC be any contact manifold on a ball. So that's a contact ball. Contact ball. And now, inside of it, we pick the following two things. We first pick the embedding phi, an embedding of a disk, so that's dn minus 1, with its standard contact structure embedded inside of BC. So that's contact. And smoothly standard. Smoothly standard, I mean, it is just a ball. You take this flat disk, and then you take another flat disk inside the flat disk. So that's isotopic to that. And then you pick a Legendrian sphere Sn inside of the ball. So this is a sphere, which has dimension n, and this is Legendrian. OK. So what is the standard situation in a smooth Whitney trick? You have two submanifolds. They intersect. Bummer. So then you try to find some kind of Whitney disk and then push along that one so that the intersection disappears. So mostly the Whitney trick is telling you every time my algebra, algebraic topology, algebraic intersection theory, tells me that I can remove the intersection, then I can actually geometrically do so. Okay? This statement is the same. Here we have a disk which is smoothly standard and a Legendrian sphere, and let me also say smoothly standard. And by that I mean a smooth sphere anywhere in the ball embedded as in a knot away from that disk. So as smooth embeddings, there is an isotopy that separates them. As smooth embeddings, this will just be a flat disk, and this will be a sphere far away. Okay? So now the claim is that this is a contact manifold, this is a Legendrian, then there exists a contact isotopy, so there exists phi t, such that at the beginning it's just this phi 0, and at the end, it's going to be an embedding, which is disjoint from the sphere. So then there exists phi t inside of this, and this is a contact isotopy, such that phi 1 of the disk has image absolutely disjoint from lambda. OK. So my brain took a while to get accustomed to this kind of setup. So first of all, this differs from the classical four-dimensional Whitney trick in that the two manifolds have different dimension, and the intersection is not a bunch of points. Now, the intersection is, however, smoothly removable. So there you have that hypothesis. From the viewpoint of smooth topology, algebraic topology certainly, you know you can remove the intersection. And the question is, can you remove that intersection at the contact level? Now, it's very important that one of them is a contact manifold and the other is a Legendrian manifold. We have several counterexamples that this could not be true if instead of a contact codimension 2 manifold, this was an hypersurface. So imagine you have a germ of an overtwisted disk, then you know that this such thing cannot exist, or otherwise every manifold would be overtwisted. Okay? So this is sharp. This is as sharp as I could think. This is contact, this is Legendrian. What is intersection? Well, this is codimension 2, so the intersection is going to be at codimension 2 inside of here, if you assume transverse. So it's an n-2 dimensional intersection. Okay? So in the case where you have a Legendrian sphere, it's just a bunch of points, but in dimension 5. But if you have like an S3 as a Legendrian instead of S9, say, that's going to be a one-dimensional manifold. However, again, smoothly you know you can remove that. So the paper that it's put on the archive has as a title, The Legendrian Whitney Trick. Because that's really what's new, and that's really what requires like all the patience of tweaking Hamiltonians. And I could present the proof of that. I've presented it sometimes, but I mean, the answer is you need to find an isotopy that does that, and you go and do it. And it's just like you take this Hamiltonian that does this, another Hamiltonian that does that, a cutoff function that cuts it off, and then you adjust the constants, and at the end you have it. So my guess was you don't necessarily want to hear that in detail. If you want, go to the paper or ask me later. OK, let's conclude the talk by assuming that this theorem is true and explaining to you how to conclude that theorem. OK? Chris?
Does smoothly removable here mean something other than just that you have an embedding of a disk, so you track it?
Oh, no, rel boundary. Everything is rel boundary. Yeah. Yeah, sorry. So, yes. Yeah, sorry. And proper, this isotopy, so this is rel boundary. Yeah. It is a full H principle relative to the boundary and could be made parametric. So this is the ball. The disk is this one. Well, it's not really this one, but I mean, it's a codimension 2 disk in here. So you can think of it as a transverse arc. So that would be the D. And well, the Legendrian will be something flying up in here. It's very hard to draw in dimension 3 because they actually don't intersect in dimension 3. But OK. So yeah, let's use this theorem to conclude that one. The proof is, I don't know. I find it funny. Well, it's the same proof as like my existence proof in dimension 5, which it's clearly that, OK, the proof works, but there must be a better way. But here goes the proof. It is inspired by the following 3-dimensional idea. Imagine I have a knot, because that's what we have here. Imagine you have a knot, and you want to make it transverse. Imagine you don't want to do this by hand. You want some powerful machinery to do that for you. Here's a way to do it. Insert an over-twisted disk, and now use an H principle for over-twisted manifolds that tells you that this knot, by H principle magical, will like wrap around that disk, do something crazy, and be transverse at the end of the day. OK? So if you've ever done that in 3D, when you have an over-twisted disk and you look at its boundary, you can connect some that with a Legendrian, and what it does is a stabilization. And if you think of a stabilization as a wrinkle is precisely what you need to make anything smooth actually transverse or Legendrian. OK? So the idea is to say, well, I don't know how to make my knot transverse. I'm going to insert an over-twisted disk far away from it, use the H principle. The knot in this isotopy will go and like wrap around the disk and do whatever it wants. And then I have a transverse knot. Great. But it's not in the manifold that I wanted. Maybe I was in standard S3, and now I am in an over-twisted S3, which has no merit whatsoever to prove H principles and things which have H principles. OK, so what's the idea? The idea is that maybe what happened is that the disk was not used entirely, only half of it was used. So this idea comes from the theory of bypasses in convex surfaces, where you realize that in order to stabilize a Legendrian, you don't need a whole over-twisted disk, you only need half of an over-twisted disk. That's this insertion of a bypass. So the idea is, OK, I'm going to define a higher dimensional bypass and then use it. Except that Onda already did that, like define it, and it doesn't work. Because every time you use this higher dimensional bypass, the submanifold itself becomes over-twisted, and you really cannot get rid of the intersections there. Or I don't know how, and he doesn't know either, I guess. Anyhow, so the idea is, OK, I'm going to do the following. I'm going to insert a full over-twisted disk, let the thing do whatever it wants, and then make sure that this resulting embedding intersects in a way that I can now isotope it back using only half of the over-twisted disk. And I have 2 minutes to explain what the key point is. So the key point is the following. You start, imagine that you start with your y and connect some with an over-twisted sphere. Now, the over-twisted sphere, imagine it's in the same formal class. The key thing is that this sphere can be described in a very specific manner. It can either be described as a +1 surgery on a stabilized Legendrian, or if you wish, it can be described as an open book whose page is T star as n. I promised Agustina I would say the word once. So this is an open book, and the monodromy is a standard den twist. That's the den twist -1. What's the key point? The key point is that if you are in this manifold and you're able to avoid this, and this is a Legendrian, so in this open book, suppose that you're able to avoid that Legendrian. Either because it's this page, which clearly it's what makes the thing over twisted, because if this was standard, that would be the standard sphere. The monodromy, it tells you how to close. So if you're able to get rid and never touch a page, then you just cut along that page and push off like that. Am I making sense? Like the difference between the standard sphere and the over-twisted sphere is that you start with T star as n, and then you take the mapping torus either with a positive or a negative den twist. If you're able to avoid a whole page, which in here just means the zero section, and then you use the Liouville flow, then you can just, well, avoid the page and then isotope back such that this was a standard sphere. If you wish, glue differently. Okay? From the viewpoint of surgeries, if I do a +1 surgery on a stabilized Legendrian, and then I can make sure that I never touch that stabilized Legendrian, and I can get rid of any intersections that I had there, then you just undo the surgery with Handel slides. Okay? So this is where the secret Legendrian was. It's, well, let me use it to create an over-twisted ambient space, apply the H principle, and then I have the issue that my resulting context submanifold will touch this sphere a lot. So, well, then use the Whitney trick. So use Whitney. So that's this Legendrian Whitney trick over there. So this is Legendrian Whitney trick, which tells you that by this theorem, this could be avoided, and then your initial M, the initial M, now lives again in your initial Y. Okay. And I want to be fair to the clock, so I'm going to finish the talk here. If you have any questions, you're more than welcome to ask.